Hey, everybody. Welcome back to the show. My name's Todd Fortier. I'm a senior solutions architect at AWS, and I'm happy to be hosting AWS On Air this week. With me is Jasmine, my co-host. Hey, Jasmine, welcome back to the show.
Thank you. Delighted to be here yet again.
Cool. And with us, we have Zia Mohammed and Jordan Sullivan from the Amazon Braket team. We're going to talk about some new features from Amazon Braket. So I'm excited to kind of learn about quantum computing. Hopefully you can kind of simplify it enough for me. I know maybe some of our guests watching the show know about quantum computing, but yeah, I'm excited to learn about it. So maybe a basic softball question, like since I queued it up with ignorance, what is quantum computing?
Well, do you want to take this one, Zia, or shall I?
Go for it, Jordan. Sometimes I wonder too.
Yeah, okay, I guess because I used to do research in quantum computing, maybe I should answer this question. So basically, quantum computing is a new paradigm for doing computation where the kind of basic rules that you're dealing with are a little bit different than our normal traditional computers, which we call classical computers in quantum computing. There's like quantum and classical. So basically you have access to a few different properties on the quantum scale. So one of them is superposition. So that's the idea that things can be in two different states at once. So if you've ever heard of like Schrodinger's cat, it's like in a superposition of alive and dead, it's that kind of thing. Then you have entanglement, and this is where if you bring particles really, really close together, you can make them correlated with each other. So when you take them really, really far apart, and you like measure the state of one of them, like you measure like what its spin is or something like that, you instantly know what the state of the other one is. And Einstein called that spooky action at a distance, which is a very whimsical name. And then you also have interference, which is a really weird one. It's kind of difficult to explain, but like essentially quantum states are probabilistic. And the way that we describe the probability of finding particular states is actually with the math that we use to describe waves. So you can, just like in sine waves or waves on the ocean, you can have waves that constructively interfere. Like if they're just in phase the right way, both of them are going up here, you get a larger wave. Or you can have them destructively interfere, so cancel out. You got one coming up and one going down, and you end up with flat states. So what that means in the context of quantum computing is that you can have quantum interference where particular states are impossible because they have canceled out the probabilities of getting that state. Or you can have other states that are constructively interfering, and so the probability of finding those states is higher. So basically, quantum computing is trying to design algorithms so that the correct solution to your problem is probabilistically amplified and the incorrect solutions are canceled out. So that's quantum computing in a nutshell.
Wow. I think I remember on a airplane once reading an article about quantum physics. And the only thing I took from that article is like when you were saying probabilistic, that the only point you can measure the actual measurement is at the point of waveform collapsing. And that's where you can determine the state of something. I don't know if I'm making any sense or if I understood what that meant, but some of the things, so
you use the words.
I'm using the right words. Right. So it's really the concept, just to kind of summarize, make sure I understand. So it's taking some of the quantum physics principles and applying them algorithmically in computing so that we can achieve better outcomes in those algorithms.
Yeah, so there's like basically certain types of problems where we expect to get an exponential speed up over classical computers. We don't know all of the possible things that's going to be true for because we have only kind of small versions of the machines that we're ultimately going to use. So like a lot of the work that's been done to figure out what types of problems are going to be way more efficient on quantum computers basically kind of assumes much, much larger scale and higher quality quantum computers than we have available right now, basically like less error prone than the ones we have right now. So there's probably a lot of applications that we just don't know about yet, but we already know of a bunch. So that's...
Sure. So the engineering of the computer itself is fundamentally different than the engineering of what we would typically consider as a computer or a server or, chips and things like that. And Amazon has made those very highly engineered, very super sciencey computers available to customers through a service called Amazon Braket.
That is exactly right. Yep.
Cool. And so we're going to go through some new features that Amazon Brackets launched. I know one of them is queue visibility. So because there's a limited set of computers in the world, you have to be queued to use it. So now you can see where you're at in your queue. Hopefully I didn't bust your announcement there.
Spot on.
But two, Zia, you said you wanted to get into the developer experience as well. So we got some other cool stuff.
Yeah. I think exactly to your point, Amazon Braket is a way for anyone around the world using the cloud to access these quantum computers. They're not particularly the size of your laptop. Some of them might be size of desks or even larger. And imagine shipping one of those on Prime or something. It's quite difficult. So I'll talk about the different types of devices as well. But these computers are really useful for very specific types of problems.
So the it kind of makes me think of like the old computers of the that predate probably most of us here on this call, and they were just big like walls of like you had to use punch cards and do all this stuff. And we're kind of in that state now with quantum computing, where they're kind of large, but the technology is advancing. Is there ever a time we'll see quantum computers at home or in other devices and small? I mean, I would presume that's the trajectory here.
Well, it's a bit too early to say.
Yeah.
I don't think it's something that we necessarily know. I've heard a lot of quantum scientists say no, they don't think it's ever really going to get to that point, mostly because like it's a very specialized machine. So I mean, you can kind of think of it. We'll often use the analogy of GPUs, but then if you use that analogy, you're like, well, people have gaming laptops, right? So maybe people will eventually have a need for super high powered quantum devices, but I think we just don't know, honestly.
Cool. Yeah. So we don't know really the trajectory, but here's one thing I do know. Amazon will be there exposing those features through Amazon Braket, and you guys will be working on it.
Yep.
And one of the things to keep in mind too of like, what do people use quantum computers for, right? These algorithms and these complex problems that, Jordan alluded to as well are really like, imagine trying to do a traveling salesman problem or financial optimization. You're not simply doing basic calculations of like what is 2 + 2, something that you'd use your regular computer for. If you're trying to simulate, drug discovery or being able to, be like, hey, if I have this element and that element and I mix them together, what will it look like? So it's more complex problems that quantum computers really help serve.
Yeah, I think I remember reading something about fraud detection as a use case for quantum computing and how algorithmically trying to get better at detecting certain patterns in fraud. Maybe someday those little captchas that we have to fill out will be powered by quantum computing. Who knows? But maybe that's too small. Hey, so Zia, you brought you have a demo for us, right? Is that right? You're going to share some of those features. Yeah. How about we
Live
bring up?
demo, so
Let's bring up that screen and see what we're looking at and see it in action.
Cool. I think everyone can see my screen.
Of course.
Right. Yep.
So basically, I'm just going to be talking about Amazon Braket, which is our quantum computing service. I'll be talking about this queue visibility feature that we launched, and I'll be walking through just generally how do you use Amazon Braket and what are some of the usability things that we've made available. So right on the console home, simply logging into AWS, I can either type in Amazon Braket or I have it recently visited. So I'll just click here. Oops, see, this is how you know it's a live demo.
Oh,
now
yeah.
I need to log in.
Happens every time. It's all good. I've done so many demos over the course of my developer career, and I can tell you without a doubt, most of them have had some hitch in the giddy up. That's for sure.
That's how you know it's real.
Yeah, exactly.
We're live.
Exactly.
We're coming
not
live.
bots.
Speaking of being live, we're getting some questions in here. Anybody want to answer some questions from the audience?
So I've gone ahead and I've clicked on the Amazon Braket dashboard. And so when I come to Amazon Braket, we have a welcome to Amazon Braket page. I'll click on this getting started. But the first thing we have is our service dashboard, which has a consolidated view for developers to see, hey, what are some new announcements? How do I get support? How do I start even programming a quantum computer? Creating a notebook, which I'll touch upon. And then I have this left-hand panel that talks about what are the devices we have. So what are these quantum computers? We'll touch upon those in a second. What is it? What are these algorithms that people run? What are all these announcements that we're having? Yeah. And so if I go ahead and I click get started, I'll be.
Hey, Zia, can I pause you just for a second before we get too deep into some of the service? I think we've got a lot of we're live. We've got a lot of
Sure.
People asking questions. Some of them very conceptual. You care if we just sort of like talk a little bit about some of those conceptuals? I think maybe we jumped into the demo a little bit quickly. That's on me. So
Yeah, I think
have
we
some
touched on
questions
this
about like
first one already.
what's that?
I think we touched on this first one already.
We
That's
did
just
touch on the
about
computers
screen.
being in the home. There's some people, just to recap that answer, there's some debate on whether or not the technology will advance, and some physicists are saying no, that it won't. But we have some questions about qubits. Like what's a qubit, and how does that
Yeah.
play into quantum computing?
So qubits, so similar to how computers have bits for computation, qubit just means quantum bit. And depending on the type of device that you have, I have the demo, I might as well show it. There's various devices or different types of quantum computers. And there's different topologies or different ways that you can essentially build quantum computers. There's things that use ion traps. There's things that use superconducting. And so these computers essentially cool down the device to a very low temperature to essentially get some of those quantum physics properties that Jordan mentioned. And then we also have, neutral atom based machines, which are a bunch of lasers trying to, excite particles to make them, demonstrate quantum properties. And so qubits are essentially just quantum bits, and there's multiple ways that you can essentially get them.
Okay, so just different approaches to establishing a qubit. But is a qubit a standard unit of measure?
Yeah, no, honestly, a qubit is kind of a weird concept because, I mean, if you think about it, like a bit is actually a really abstract thing. It's like the idea of like the Platonic ideal of a 1 or a 0, like an on and off, and like encoding things in binary. But like when we actually build bits in reality, like it's transistors, it's like having a bunch of electrons on a transistor, and not having the electrons there is your 0, and having them there is your 1. So much like that, in actual quantum computers, the hardware that you can use in order to get something that does the qubit things, that has superposition properties, that can get entangled, that can have quantum interference, ton of different ways you can build that. Like it just needs to be what's called a quantum 2-level system. So you can be like, okay, how about it's like we use polarized light as our qubit. We can say that, you know how like sunglasses have polarization, so they're only letting in like half of the light. So you can say that like vertically polarized light is your 0 and horizontally polarized light is your 1. Or you could say like, I'm going to use an electron and say like my up is my spin up electron is a 0 and my spin down electron is a 1. So there's like a ton of different kind of properties that you can use in quantum states to get something that behaves like a qubit. So it's this kind of very general idea, and I think we just honestly don't know yet what is going to be the best way to build a qubit at scale. Like you can build really good individual qubits, but the trick is to actually scale that up and build something that is useful and ultimately like on a commercial scale.
Yeah, it's so fascinating. So I imagine, we're through Amazon Braket, we're exposing this sort of very new paradigm of quantum computing, but we presumably give some level of control through a programming language, and we allow customers to program to these qubits and these machines. Are there specific languages that we support or that customers use to develop this, and what are some of the advancements there?
Yeah, I think the Braket service essentially has its own SDK as well, which is Python based. It's available in other languages as well. And then there's various quantum frameworks out there. So essentially Python based SDKs, that one is Braket, another one is Qiskit. There's a bunch of different frameworks that we support on Amazon Braket. And so if you're a Python developer or you have some access to, standard programming languages, these frameworks enable you to learn more about quantum computers and actually run programs on them. And I'll be showing that in a sec too in a getting started demo.
Yeah, just to I don't want to pepper you with a bunch of questions before we get. I just want to let the audience know that these are coming in live, so continue bringing in the questions, and we're going to continue trying to answer them as we go. But I know I kind of want to see this in action. I'm eager to see what this means at Amazon.
Sure. So again, Braket allows you to build your algorithms, build your service through Jupyter notebooks. You're able to test them on quantum simulators as well as quantum devices. And so these on-demand simulators that we offer essentially mimic some of these quantum computers. And then you're able to analyze your results. So when I go to the Getting Started page, I see this dashboard. And before we get started, there's a little setup that we have to do. And this is one of the usability improvements that we added. Within these 3 steps, you'll be able to start making a notebook and set up all of the cloud permissions that you might need. So I've gone ahead and created something called a service link role, standard for cloud. I actually want to use some of these devices. It's an optional thing, but if I want to use a quantum computer, I'm just going to go ahead and accept and enable this. And then I'm actually going to create a Jupyter notebook. So the way that Amazon Braket allows you to interact with a quantum computer is through our Jupyter Lab IDE. So this interactive development environment, I'm just going to go ahead and call this testing. So Amazon Braket testing. Create a notebook, and I'll be taken to a review page. I can see that I've enabled everything, and I can click Open Notebook. Starting my notebook. While that's loading, I have the opportunity to go and explore more about Braket. So this algorithm library, that Python-based SDK that I was telling you guys about, as well as our developer guide. The developer guide is able to provide more information on what is Braket, what is quantum computing, how can you actually get started with it. And so while this notebook is loading, let's go ahead and visit this devices page. I think there were a lot of people who are curious about what kind of quantum computers we have, what are they, how do they work. And so we have a multitude of hardware providers. So IonQ is one, Oxford Quantum Circuits is another, Quera, and then Rigetti. Each one of these offer a different type of quantum computer, and that is available in this description. If I'm curious more about it, I can actually go ahead and click on one of the devices. When I click on this device, it'll tell me, okay, hey, what kind of model quantum computer is this? Is it online? What's the device ARN? So how do I access it? And then it'll give me some details about it. So for each one of these devices, we explain how it works, how people can access it, who's the hardware provider, when is it available, where is it located, and additional information about it. The interesting thing to note is these are finite resources. So similar to how you can just go on fly and provision an EC2 instance, and there's a bunch of compute resources sitting in a data center, quantum computers don't have that luxury yet. And so somewhere out there in Maryland, there is sitting a computer that you have access to. If you think back to what I said earlier, some of these might not be laptop sized and they might be a lot bigger. And so being able to gain access to them through the cloud is one way that we allow customers to play around with quantum computers.
What a crazy concept. That concept to me is crazy, that there are only so many of these computers in the world and that our customers can log on to AWS and get access to something that was still like relatively like a new paradigm in computing through Amazon Braket. That just kind of blows my mind.
Yeah, actually, you should bring up, Zia, can you bring up some pictures of the devices that we're talking about? Like if you go to our devices page, you can actually see like what the quantum computers actually look like. It's very cool. It's very sci-fi. Oh, no, I meant the actual like photographs, not the, I mean, the topology is very pretty. It looks like a mandala, but like.
Oh, yes. Yeah, we'll get to that.
Let's see some pictures of these things.
Yeah.
I think this is actually their website. Were you talking about the Amazon Braket one or?
Oh, I mean, you can go either on the Braket website or like, I'm sure they got pictures on the IonQ one. But like I know they have ones on our devices.
Oh, here's a good one.
That's a diagram. I'm talking about pictures here.
We want to see what it looks like. It's like finding
Go
a
to the Braket
unicorn.
homepage. You can find it.
I can just do a quick search. I'm wondering where to check.
Just go to the Braket product page.
Mm-hmm.
It's on Braket. Oh, our quantum computing
You've
survey.
been here before, right? It looks like it.
Yeah, seems like it. Okay. We have the pictures here. Oh, here.
Yeah,
perfect.
There we go.
Zoom, zoom, zoom.
What am I even looking at?
We've zoomed in. Maybe I did too big.
Scroll.
Scroll.
There
Okay,
we
there you
go.
go.
Yeah, so this is an ion trap actually. So it's really hard to see, I think, but if you zoom in more, if you just like Control plus a few times, yeah, then you can actually see on the right hand one here.
Yeah.
We'll find it again.
Here we
Yeah,
go.
okay, yeah, here we go. So all of those little like glowing dots are ions. So they're charged particles and they're trapped in lasers. So it's called an ion trap. So like you can access this. This is an actual thing that you can control. You can control what these ions are doing in Maryland.
What?
Wow.
That is cool. Hey, thanks for finding that, Zia. That's
Sure.
it is cool to see it though, right? Because I think it's so often it's easy to get lost conceptually in the physics and the quantum and like even when I read about quantum physics, it's like, is this real? It's like, how is it? But okay, like, what am we actually talking about here? Like, what's tangible in this? But to see this an actual physical, piece of hardware that is implementing some of the wildest stuff I've ever heard is cool. It's very cool.
Yeah.
All right, I'll stop interrupting your demo.
That's okay.
Yeah,
That's how, like Nick just told everybody in the comments, that's how you know that we're live. So if you're just joining us, this is AWS On Air. We are giving you our weekly launches and latest updates from AWS, all things cloud computing through live demos. Today, we're talking about quantum computing. Jordan has just gone through and given us a very high level of description of it, but then some of the nitty-gritty details. And then Zaya here is showing us around in the AWS console and where to find it, some of their latest features, but we stopped to see, is this actually real? What does it look like? And so we see some lasers firing from all of these finite resources in the world. I actually did a quick search to see how many quantum computers are in the world, and the top results say only between 150 and 200. So it's really awesome that you can go into the AWS console and Amazon Braket and queue up some resources for yourself if you want to do some of these really complex things.
Yeah, and speaking of Q, should we get back to our demo here?
Queue up the demo.
Queue it up.
Demo.
I'll close out of this. Yeah, because these are finite machines and you don't have access to them, one of the things that we wanted to do was really provide customers ability to see, hey, I've just gone and submitted a program, and we'll actually go and do that in a second too. But do I have to wait? Like, why isn't my program submitted? And so one of the things we exposed for customers was queue depths. So being able to see, hey, I've submitted a program to a quantum computer, where in line am I? And so being able to see that for a task or a hybrid job. Hybrid job is a bit more of a complex topic, but essentially it's when you have a classical computer and a quantum computer and you want, co-processing between them, hybrid jobs is our mechanism for customers to actually run those programs. And so for each one of these devices that we have, you're able to see, hey, how many tasks are queued, how many priority tasks are queued, and how many hybrid jobs are queued. And for each one of these as well, you saw the pictures, but it's interesting to see, the information about them. So this is a 79 qubit quantum computer, and you can see the topology. When a lot of people are doing these calculations.
To be clear, the topology here just means how all the qubits are connected to each other.
Yep. The topology explains just that. And a lot of researchers are really curious about, hey, each one of these qubits, what are the properties that it has? What are the error rates that it have? And so scrolling down, we have these calibration windows as well that show, hey, what is this T1 time? Okay, it's this. Hey, what's this T2 time? What is that? And you're able to see all of this information when programming a quantum computer. Because right now at that level, each quantum computer is unique. And each qubit that you have has different error rates, different fidelities, and all of this information is useful for people who are writing these quantum programs.
Yeah, and this is super helpful, right? Because we're talking about something that can be hard to digest, right? If you're new to it, right? If you're not a researcher working in a lab and focusing on this stuff. But the fact that through this console, we've exposed this information and made it consumable for customers, I think is really cool. And so you're saying with this Q thing, before customers would just submit a program and then it would you would get some results at some point once it completed. And now you can kind of get a sense of, okay, I'm going to be waiting a while, or maybe, hey, I'm next in line. Let's get rocking.
Yeah, you can either come to the console or check programmatically as well where in the queue you stand. And so when we go and submit a couple devices or a couple circuits or quantum circuits, programs essentially, we'll be able to see some of that.
Cool. Are you going to submit a quantum
circuit? Let's go and do it.
Oh, nice.
So I'll go back to my notebooks here. And I can see that my notebook is actually created. And so when I click on the URL, it'll open a new tab. This is that Jupyter Lab environment. We have examples that you can use to get started, but let's say you've already gone through all of these examples and you want something, next level, and you're wondering, hey, what else can I do? We have an algorithm library as well that basically explores and says, hey, here's a bunch of algorithms or fundamental things in quantum computing. Here's what they are. And you can actually view the GitHub code, download it locally, or you can run it in this Jupyter Lab environment. And so if we go back to this Jupyter Lab, let me close out of some of these news things. You'll be able to see we have a bunch of examples on the home page as well as right here. And so I can click on getting started and I'll see, we have 5 examples here, or I can just click start on Braket. This is one of the usability enhancements that we added because we heard from customers that, hey, going through this notebook, I might not be able to find things. I really want an easier way to get started. And so we have a Hello World tutorial where we're essentially building a circuit. So a quantum circuit is a collection of logic gates. So similar to, you brought up computers in the 60s, there were AND gates, OR gates, these fundamental logic gates. We have them in quantum as well. And a collection of them is what's known as a quantum circuit. And so I'm going to go ahead and just click run all rather than running each individual cell. And what this will do is, I believe this is running on a local simulator, but we can actually run it on a quantum computer as well.
So we can simulate the notebook. So this is a very similar experience to like Sage Notebook or SageMaker, Sage Notebooks, where we can kind of run individual blocks, but then we can also run all blocks in it at the same time. And so you just said something that like simulator, so we can kind of simulate just to make sure functionally our code is working. But then when we really want the horsepower, we're going to kick it over to the quantum computer. Yeah,
for some circuits it really depends on the circuit or the program and the level of complexity that you want. So we can actually use local simulators or even simulators that Amazon has. So, we have SV1, which is a 34-qubit simulator offered through AWS. And these are essentially just running on EC2 clusters, so classical compute. And up to a certain point, they simulate what a quantum computer can do. And so right here, we ended up running a very simple circuit. It's a fundamental circuit on a simulator, but I ran this locally. I'm going to skip ahead to, I think it's that's simulators on a QPU device. And I'm going to take that same circuit and I'm going to go ahead and run it on a quantum computer. Let's see which quantum computer it's calling. And for those familiar with Python, I believe someone was asking, hey, what's the programming language for this? Those familiar with Python will really recognize the syntax. We're importing a bunch of libraries. We're importing devices. And so let's see what device this is using. Oh, this is cool. This is a circuit map. So each one of those quantum circuits that we're building, this is a Hadamard gate or an H gate. And so similar to how you had those classical gates, we have these quantum gates. And so here you've written the quantum circuit, you visualized what it looks like. To your point, Todd, hey, let's actually simulate it, see how it looks. This is the result that we get. And then let's actually run it on a quantum computing machine. And so I can see that, hey, I've submitted this, but there's a queue. And so we're showing the customer right now, hey, you've just submitted your circuit. It's been created, but there's a queue of 6 people in front of you. And so while we can't expect this to run right now, I can actually call and be like, hey, what's my queue position? And so providing this level of transparency to the customer, rather than just having them wait, is something that queue visibility really allows for. In addition, one of the cool things about Braket is you have one programming language to run on multiple machines. So you don't have to go and learn a new programming language for Rigetti. You don't have to learn it for IonQ. One of the things that we've done is through Braket, we're able to submit that same circuit that I wrote up here. Where did it go? This one. And in parallel, I was able to submit it on the Rigetti device and figure out, hey, I'm in position 7, but then also this IonQ device. And here I'm in position 14 right now. And so when these run, actually, I think this demo runs it on all of them. So the cool thing about it is when I go back to this screen, I can see it programmatically, but I can also see it in the console. When I go to the device, I'll actually be able to see, hey, this is the queue depth where I'm at. So essentially, it makes it friendly for customers looking to run things programmatically, but there's also this visual aid through the console.
Yeah, very cool. So yeah, I know we are getting close to running out of time, so I just want to make sure that we touch on some key points. We don't miss anything. Just to recap a little bit, what you've just showed us is, one, Amazon has created a service to expose quantum computing to customers. It's abstracted some of the low-level details of that to make it easier for customers to understand how to use these services. They can actually see where they are in queue if they submit circuits to these quantum computers. But then also we have a library, an extensive library of algorithms that you can play with to get started. We have guides, we have documentation baked in, both and on our guide, our documentation website, SDKs and CDKs and all that cool stuff, I imagine, also available to customers. Is there anything else that you want to make sure that customers understand before we wrap up?
Yeah, thanks for asking. One thing that we actually recently rolled out for this console as well was localization. Everyone around the world should have access to quantum computing, no matter where they are. And if you go to this settings icon right here, we have support for a plethora of languages, from Bahasa Indonesian all the way to Korean, French, Japanese. And so if I actually click on one of these, I'll just use Korean, for example, my entire console is now localized. So, if I'm overseas or if I'm in a different, region and I want to do a demo or I want to use Amazon Braket in my native language, why should I have a barrier to do that? And so with this localization feature, we're able to, I don't speak Korean, so I'm randomly clicking now, but every single page and even some of these statuses, you'll notice, have been translated to essentially provide localization. And so I'll change this back to English.
It's one of the things I love about AWS and working at AWS is how it can take something so complicated and then make it accessible, right? Make it accessible both technically, but then also locally. Very cool. This is an awesome demo. I could probably talk about this all day. I do nerd out on physics every once in a while, like in airports and stuff. But I know we don't have that much time. So I want to thank you, Jordan and Zia, for coming onto the show and giving an awesome demo and talking about something that can be really difficult to talk about sometimes, but you guys made it easy. And so this is great. Thank you.
Yeah, it's a pleasure to be here. And I just want to +1 to the person in the chat that was thanking the amazing ASL translators, interpreters for dealing with the very, very difficult jargon of this topic. It is not easy to have to do on the fly. So hats off to those folks.
Absolutely. Thank you so much, Brian and BL. Amazing as always. Impressive stuff.
Right.
Awesome. So Jasmine, great show. Awesome show.
It's been a great show. Where can everyone learn more about Amazon Braket?
Yeah, I think our folks who are in the chat should be able to drop links to cool blog posts about this kind of stuff, our recent improvements and general cool things that you can do with quantum computers. So watch out in the chat for those.
Yeah, and thank you for the questions, everybody in the chat. Really good questions and good engagement. I hope this was an exciting session. Jasmine, few closing remarks. We got reInvent coming up. You said 31 days. Well, let's say 30 and a half days now that we've done this session. People can register right now. They can get start favoriting their favorite sessions, get signed up for some of the fun activities. AWS On Air is going to be there with a roaming camera crew. It's going to be very fun and exciting. Anything else, Jasmine, you want everybody to know?
Please complete our survey. Please take 5 minutes to let us know what it is that you like about the show. If you love this session on quantum computing, let us know that in the quick survey as well, because we would love to have Zia and Jordan back, because I know I thoroughly enjoyed this session and just learning more about that. So we do have some AWS credits for the first 50 respondents. And so you get $10 to get into the AWS console and build some new things and learn about AWS and hopefully launch some fun things for yourself.
Yeah, Jordan, Zia, thank you so much again. We're going to let you go, get back to like quantum computing, designing some circuits. I can't wait to hear more and learn more. Thanks again.
Yeah.
Appreciate it.
Yeah, and thanks to our audience as well. We could not have a show without the audience.